I got 3 examples that are, I think, model what's on the assignment pretty well. Okay, if you can do these 3 problems, you're in great shape. This is the goal for this stuff, for the differential stuff. So let's look at one like this. Now, the radius of a spherical hailstone caught in an updraft increases from 18 millimeters to 22 millimeters. Find the approximate change in the volume of the hailstone. Okay. So what's our important equation here probably? Okay. So what, remind me, what is that again? What's volume of a sphere? Pi r cubed, or yeah, r cubed. There we go. Okay. All right. So what do we know here? Okay. So yeah, what's going to be our value for r? $18, right? We're starting at 18. Does that make sense? Okay. So r equals 18 millimeters. I guess we'll put the units in. That's fine. What's our bump? And what do I call that? dr, right? Okay. Positive 4.
Nevaeh Castillo and Matilda Allen to the office, please. Nevaeh Castillo and Matilda Allen to the office, please.
Okay, good. What are we trying to find here? Change in volume. So what is that? dV, right? What's delta V? That's a little different. What is delta V? That's different than what's being asked here. What's delta V? This is the exact change, right? That's the actual change. dV is the approximate change where we can just use a differential, right? Okay, so then what's the differential that's going to give us this answer? So we're trying to find, let me write that down. So you guys correctly told me dV is what we're trying to find. What is dV? Okay, you're right. So, but in general, though, what would we say it is just in general, before we even calculate a derivative? dV is equal to, well, something dr, but what do we always say about dV? Like, just in general, we say that dy equals what? It's just the differential form of a derivative, right? So f prime of x times dx, right? Okay, so what is dV here then? V prime of, what's my input? Okay, right, so V prime of r times dr, right? Okay, and what is V prime of r? Okay, good, that's going to give us our 4 pi r squared, right? Make sense? Right? Okay, all we have to do is plug in the values. So what are our values? We get 4 pi times what? 18 squared times, right? And if I want to put the units in, I got a millimeters there and a millimeters there. Because that's what we started with, right? We started at a value of 18 and we bumped to 22. And we want to estimate when we bump the radius up by 4, well, how's that going to bump the volume? What's the approximate change in the volume? Okay, so that's going to give us just some number. We're going to get, what's that going to be? 324, 648, 1296. So we're going to get something like, I'm probably not going to get this right. Oh, I know I could do it. So it's just going to be 5200 minus 16. So 5184, I guess, is what we'd get. What would my units be? Yeah, cubic millimeters. I might. Oh, and there's pi there, right?
That's what I got.
Yeah, that's right.
That is correct. Okay.
You did 16 times 324.
What's that?
You did 16 times 324.
What I just did, I did 324. Yeah, 16 times 324. Yeah. So is that big or not? I mean, we wouldn't really know unless we looked at it as a relative change, right? Okay, but that's how much we would expect the volume to increase, going from 18 millimeters to 22 millimeters. That's a big hailstone, actually, isn't it? I mean, that's like a Texas-sized one. You're talking about almost a 2-inch diameter hailstone there, right? So that's pretty big. There were some. Have you guys, anybody driven through Wallowa like in the last few months? Oh, so you saw the damage? Yeah, I mean, it just tore that place apart. That was Wallowa, yeah, where the wind was blowing the hailstones in. Every window in town was broken. It was crazy, yeah. And then siding was damaged. I mean, you look at some of these houses, and they just looked like they'd been shot by a giant shotgun or something. It was crazy. Okay, so does that part make sense? Okay. So then we found the approximate change in volume of the hailstone. Estimate the percent change in the mass of the hailstone. Well, I changed to mass, but what's our trick here? Hailstones are made of ice. Is ice uniformly dense? Yeah, for the most part, right? I mean, almost exactly uniformly dense. So instead of mass, what could we swap that for? Volume, right? Volume and mass are going to be proportional. So we could even just do this. We could swap that for volume and get the same answer, right? Okay, so we got to find that then, the percent change in the volume. Well, how do I write percent? I mean, when we say percent change, it's just relative change written as a decimal. So what's relative? Well, what's the relative change in volume going to be? What are we looking for here? dV over V, right? That's the relative change in volume. We're going to compare the change in volume to the size of the volume to see if it really is big or not, right? So that's what we're looking for here. Okay, well, dV over V is what? So rather than just plug in numbers, let's simplify that expression. dV, you already calculated, was 4 pi r squared, dr, divided by volume was 4/3 pi r cubed. So there's a lot of cancellation. The r squareds cancel, the pi's cancel, the 4's cancel. So I'm going to get a single r left on the bottom. I get a 1 over 1/3, so that's a 3, right? So I just end up getting 3 dr over r, which is almost most easily contemplated if you think about it as 3 times dr over r. And you could have probably predicted that. You're starting to get a little bit of intuition here about this stuff. We kind of talked a little bit about this yesterday. Not that you have to know this. I mean, the math will tell you every time. But how could you have predicted that was going to be a 3 there? Because it's volume instead of radius, right? So you're measuring, instead of just measuring a linear measurement, you're measuring, a linear goes to area. So now it's a square, goes to volume. So I've I've taken the effects of that linear measurement and I've tripled it because I've got to measure 3 different dimensions this time instead of just one. So you can sort of anticipate you're going to get a 3 there. If you lived in a weird universe where there were 4 extended spatial dimensions and you calculated the 4 volume of this thing, what would the answer have been? Would have been a 4, yeah. If we calculated surface area, what would that probably have been? A 2, yeah, okay. And then all we have to do now is just plug in these values, which we know, right? dr was 4. Was it? Yeah, it was 4, not 0.4. Over 18. And you get 12 over 18, which is, what did we get here? 2/3? Did I do that right? Yeah. 2/3. Now notice what happens to the units. What happens to the units? They cancel, and they have to, right? Because you're talking about a relative amount. You're not talking, we don't want to have units in there. We just want to have a percent, right? So 2/3, which is equal to, what would that, well, that's big. So it increases by about 67%. Okay, increases a lot. How come it increases a lot? Well, because that shell has a lot of volume. Thank you. Okay, okay, don't let me forget to pass those out. I'll pass those out in a second. Okay, make sense? Is that approximation, what do you think? Is that likely to be super accurate? I'd be a little suspicious because 4 millimeters is quite a bit compared to 18, right? The volume increased by a lot. If the volume is increasing by 67%, I don't know. I wonder how accurate that's gonna. It would, yeah. Mm-hmm. And we'll come back and revisit this. Like if we thought about what this curve looks like for a second, volume curve, that brings up something kind of cool. So the volume curve, if this is volume and this is radius, it's just going to do something like that, isn't it? It's going to look like the positive part of a cubic function, right? And so if we're picking some value here, some point of tangency, and creating a linear approximation, it's going to be an underestimation, isn't it? Right? How come? We don't really have the words right now, but do you see why the green tangent line is always going to under approximate a change in volume? The volume is going to grow by a little bit more than the green line predicts. What about the shape of the curve is causing that? Cubed, yeah. It's the fact, we don't have this is coming up real soon, but the term we're going to use pretty soon is that the concavity of the purple function is positive. It tends to be concave up, right? Concave up just means that a tangent to the curve is going to sit below the curve. Okay? And anytime you have a positive concavity on a function, and we don't know how to calculate that or what that means yet, but we will soon. That would mean that any approximation is an underestimate if the concavity is negative. So the tangent line sits on top of the curve, then it would be an underestimate. Okay? All right, moving on. Questions on that one? Does that make sense? Okay. How about one like that? The area of an equilateral triangle of side length x can be calculated just from the side length. That's the formula. Square root of 3 over 4 times x squared. X can be measured with an error of at most 0.2%. What is the maximum corresponding percentage error in computing the triangle's area? Okay. So what would that look like? If I'm calculating percentage error, what am I looking for here? What is that? So I want to know what this animal looks like. What is this? If I percentage error in computing area. Yeah, that'd be dA over A. Everybody see that? That's a percentage means relative, right? So that's a relative error for area. Relative propagated error is what it is. Calculating area. So we're trying to find dA over A. Now you look at this at first and you might think that's not enough information, right? They don't give us anything about the size of the triangle, nothing about X or how much X grew, right? But what we do know is relative error. What does this tell us? It's a percent and it's unitless, so you know it's a relative error. What's that orange thing telling us?
Is it saying that dx over x is
That's right.
22%?
Okay, so dx over x, that's relative error, measurement error in measuring x, right? This is relative measurement error, that's relative propagated error in calculating something from our measurements, okay? What is this? How would I write that? Right? Everybody get that? Because if it's 0.2%, then that corresponds to the decimal 0.002, right? Okay. We'll see a little shortcut at the end of this, but got to be careful with it. Okay, so that's all we know. How would I proceed with this? What we can do? Yeah, we got to find the differential form of the derivative. We need to find dA, don't we? Okay, so if this is A, what is dA? It'd be A prime of X dx, right? Okay. Well, what is A prime of X? Maybe I'll write that down. So okay, good. So I've got this square root of 3 over 4 that's a constant. The derivative of x squared is just 2x, right? So 2 square root of 3 over 4, the 2 and the 4 would cancel. So I get square root of 3 over 2x dx is dA then, right? Everybody see that? Okay. So dA equals square root of 3 over 2x dx divided by A is equal to square root of 3 over 4 x squared. Okay, we get some cancellation, right? We're going to get, if we look at the cancellation here, we cancel 1x, we cancel the square root of 3's in the numerator, and I get 1/2 divided by 1/4, which is 4 over 2, right? So I just end up with 2 times dx over x. I don't need to know what x is or what dx is because I know the ratio of dx over x is what's given to me. Isn't that cool? Right? Okay, so we end up with our answer then is just 2 times 0.002, which is 0.004, or 0.4%. But again, we probably could have predicted this, couldn't we? Right? Because we're moving from a length measurement to an area measurement, so that too is fairly predictable. Okay? Make sense? Okay. All right. Last one. How about this guy? Any questions on the last one? You need a second before we move on? Let me go back first. You can stare at that for a second and see if. Yes.
Is there a word like to call like how the side length is proportional to like the length, but it's not proportional. It's like it has like the side length gets bigger, the volume gets bigger, and like
It'd be a matter of like scaling is what it would be. Okay, good. All right, last one. Let's look at one like this. So the maximum allowable percent error in computing the area of a circle is 3%. So we can't exceed 3%. Find the maximum allowable percent error in measuring the radius. So what are we given here? What is this? That's dA over A, isn't it? Right? So we're given dA over A is less than or equal to, right? Less than or equal to 0.03. Oh, by the way, 0.03. Let me backtrack for just a second. Being as we're multiplying by a ratio, could we have written that as a percentage? Yeah, we could have, right? We could have just multiplied 2 times 0.2% and gotten 0.4%. Okay, you gotta be very careful with that though, because doing math with percents is a little dangerous, right? Because they're not, you really, technically, you always are dealing with a decimal, and percent is just a funky way of representing a decimal, right? Okay, but we could have, in that case. Okay, better to go to decimals though. Okay, estimate, what are we trying to estimate here? dr over r, right? So we're given the maximum allowable propagated error, and we're asked to find what's the corresponding maximum allowable measurement error. So dr over r is what, I guess, right? Okay. What kind of a area are we talking about here? Circle, okay. So then what's our equation for area? So what's dA? 2 pi r dr. Right? That's our differential, right? Okay. So how do we proceed then? What do we know to begin with? What are we starting with? Yeah, the 3% one, right? So this is what we know. I want to get to this. So I need to write that in terms of, I need to write an expression in terms of r's then, right? Write that top expression in terms of r's. That's what that'll allow me to do, okay? So dA over A looks like 2 pi r dr over pi r squared, right? And that has to be less than or equal to 0.003. There's an inequality that we can work with, and we're just trying to rewrite that in terms of dr over r, which is easy to do. The r, one r cancels, the pi's cancel, and look what we get. 2 dr over r is less than or equal to 0.003. Isn't this what we're trying to solve for right there? Right? What's my one step? Divide by 2, right? And so we end up getting dr over r has to be less than or equal to 0.0015. Okay, or dr over r is less than or equal to 0.15%. Okay, good. All right.